So it's my pleasure to introduce Andrew Goldberg, who is visiting from Microsoft Silicon Valley. Andrew works primarily in graph algorithms, and his algorithms are taught at most computer science institutions and operations research institutions, shortest path, network flows, those sorts of things. So I've known Andrew since '99, and I wrote my first paper with Andrew. And he's the one who got me interested in auction theory a long time ago, and so it's great to have him here.
Okay, thank you, Jason. So I'm going to talk about high-event VC dimension and interaction of practice and theory. And this is joint work with my colleagues at SVC, Microsoft Research, Itai Abraham, Daniel Delling, and Renato Vapnik, and Amos Fiat, who is at Tel Aviv University. And before I go to my talk, it's sort of a little bit of advertisement. I recently joined Skolkovo Institute of Science and Technology as a founding faculty fellow. It's a new university in Russia, and it's an integral part of Skolkovo innovation project, which includes some R&D labs, which are going to open startups and the university. And the university, think of it as Cornell, New York City campus. You probably heard about that. So it's something similar. It's sort of an institution, a Russian institution in international context. In particular, it's sort of modeled under Western universities, and also people are paid as in Western universities. It's built in partnership with MIT. And there's a founding faculty fellowship program where founding faculty fellows are supposed to launch the university, establish basic policy, hire initial faculty, and then sort of leave. And it has basically focus of graduate-only education and research in 5 areas, including computer science, which is part of information technologies, and there are programs to support entrepreneurship and innovation. It's expected to grow in the next 7 years or so to 200 faculty, 300 postdocs, and about 1,200 grad students. And it's now hiring, and there's a URL. And in fact, it's hiring internationally. So, okay, so now let's start with my talk. And I want to go back to scientific method, which is a basis of natural sciences. And it's an interaction of sort of observation, hypothesis or theory, and then verification of hypothesis and theory. And the way you do it in, say, physics is you make a prediction, something which haven't been observed before, and then you go and see if this is really true or not. And so this is sort of interaction of theory and experimentation. And the theory is valuable if it tells you something new. And in computer science, in algorithm design, it's sort of an interplay between mathematics of algorithms, where you have a formal model and you prove theorems about how your algorithms perform in this model. And algorithm engineering, where you try to get a good implementation of some algorithm and see how it performs on real or artificial instances. And the science of algorithmics is basically an interplay between mathematics and experimental aspects of algorithms, where you sort of get more relevant theory by doing experiments and by explaining the results of experiments, and your algorithms are hopefully provably good, so you don't have any unpleasant surprises. So this is the outline of the talk, and so let's start with motivation. So there was a lot of progress in point-to-point shortest paths, mostly due to navigation systems, location-based services, and such, which are becoming more and more used. And the problem is that on a continental size network, with tens of millions of vertices. The standard Dijkstra's algorithm, it's sort of essentially linear time, but it takes a few seconds. And that's not enough for many applications involving many users in particular. And then there was a lot of recent work making it faster. And actually, this was the work before we sort of started this work, which I'm going to talk about. And the result was greatly improved performance. You can find roots much, much faster than a millisecond, than sometimes in microseconds. And also on a mobile device, you can do it very, very quickly. And it's sort of annoying. I have a brand new car, which was brand new electronics, but when I ask for a route, it says calculating your route, and then you have to wait. And it's clear that Garmin is about 10 years behind the curve. But you can do these things very fast, and actually you'll see how fast. It's if someone, when I was starting doing this 10 years ago, told me I could do it that fast, I wouldn't have believed it.
So those figures aren't in the same units, because you quoted us 5 seconds for a regular computer and 0.1 seconds for a mobile device? Is that?
No, this is new algorithms. Even on a mobile device where you read from flash, it takes a fraction of a second. Whereas on a fast computer, all algorithm takes more. No, it's the same units. This is just new algorithm, and this is old.
But those calculations are done server side and then pushed to the mobile device, right?
No. This is done completely on a mobile device from flash.
Wow.
That's why it's so slow by modern standards. No, you really will see that. In fact, something like 100 memory access is all you need. So the model is you have a graph, and since I'm mixing theory and practice, I assume that shortest paths are unique. And actually, there will be a theorem where it will be important. And in practice, some algorithms actually require perturbing the input to make shortest paths unique, and you can do it. And then V and E is vertices and edges. And for simplicity, and also because some theory works only in undirected case, we'll assume that G is undirected. Algorithms also work for directed graphs. Some theory doesn't work as nicely for directed graphs. And then there's a weight function, which is either length or transit time or fuel consumption or whatever, some measure of length of an arc. And in this talk, we'll talk only about static problem, and the length function will capture all the modeling information. So there are interesting things about dynamic shortest path and time-dependent shortest path and so on, but they're not a subject of this talk. And you are given the graph, and then you have queries, multiple time for the same network. So Navtex spend years collecting map data, but queries you do on the same map. And given an origin destination, you want to find the shortest path from S to T. And here we'll talk about exact algorithms. Maybe you can do better with non-exact algorithms, with approximate algorithms, but you can do exact algorithms very, very fast. And also it helps debugging and modeling. For example, if you are modeling how expensive left turns are, and if you change your function and you got a different route, if the algorithm is optimal, you know that you got it because of your change in the model and not because the algorithm just stumbled on a different solution. And we're going to talk about algorithms with preprocessing. We have two phases. So you spend a long time collecting map data, so you can spend a few hours, or in fact, for modern best algorithms, it's a few minutes preprocessing the graph. And then you answer queries in real time. And preprocessing may use more resources than than queries. So queries run on production server or on a handheld device, mobile device, and preprocessing can be done on a bigger server. Or Google actually uses many servers. So let me describe one of the algorithms so that you see how fast these things are. So the transit node algorithm, which was the best algorithm during the Dymex implementation challenge a few years back, due to Bast et al., works as follows. The basic thing is the observation that if you have some area of the graph, for example, San Francisco, and you consider sufficiently long routes out of this area, there's a small number of checkpoints which you can put to cover all of these shortest routes. So in this case, it's basically highways and bridges. Note that this is not a separator. If you want to go around this checkpoint, you can. But then you will not be traveling along the shortest route. Okay? So that's the intuition. And what these guys did in their original implementation, the new one is a little different, but they divide the map into regions, a few thousand regions, and you'll see why a few thousand. And then for each region, you find a small number of access nodes. These are these things which cover sufficiently long shortest paths out of these regions. And the union of access nodes is a set of transit nodes. And you pick a few thousand of those so that you get about 10,000 here. And the reason it's 10,000 is that because 10,000 squared is a manageable number. It's a large number, but it's not too large. For example, you can store it. You can store that many values. And then they had a nice empirical discovery that there are a small number of access nodes. There are roughly 10 access nodes per each region, which is sort of amazing, but by now it's sort of established. And then preprocessing algorithm works as follows, and I'll hide the details because that's the most complicated part, but you don't need to know how it works to know how queries work. So you find access nodes for every region, you connect each vertex to its access node and compute the distance, and you compute all pairs of shortest paths between transit nodes. And as I said, this is a manageable number, so you can in fact compute and store all pairs of shortest paths between transit nodes. And then how does a long-range query work? Remember we talked about sufficiently long paths going out of the regions, and a sufficiently long path from S and T has the following form. You go from S to access node of S to access node of T to T. And conveniently, there are a small number of access nodes of S and T. You pre-computed the distances to them, and you know all pairs of distances between transit nodes. So there are about 10 values here, about 10 values here, so you need to do roughly 100 table lookups to compute the distance. Okay? So it's that fast. It's about as fast as 100 table lookups. And for local queries, you either use a multi-level approach or you use some other method to do local queries. Okay, but this should give you some idea of how fast these algorithms are. Think about 100 memory accesses. Then when we were a few years back is that we have some algorithms which are intuitive and practical. We know they work well on road networks. In fact, some of them we know they work well even in worst case because you can measure it. But there was no explanation of why they work well on these networks. And of course, it's known that they don't always work well. On some networks, even as simple networks such as take a planar grid with random uniform weights, these algorithms don't work so well on this sort of networks. So to answer why these algorithms work well on road networks, you have to answer what is mathematically a road network. And we, in a couple papers, we answered that question. We defined the notion of highway dimension, and we gave good time bounds for some algorithms, assuming this highway dimension is small. And then we got even better bound for hub labeling algorithm. And we implemented it. It sort of looked impractical, but encouraged by good bounds, we implemented it and actually find out that it gives you improved practical performance. And we also gave a model of sort of generative model of how road networks come to be. which show that under this model you get networks with constant highway dimension. And the nice thing about these results are a couple of years old, but we're now working on a journal version of these results, and we got some a better definition and some new results. So what I'm going to talk about, a lot of that is new. These papers sort of are, most of ideas are there, but they're not as nice as these newer definitions. So one nice thing is the relationship between shortest path and VC dimension. And how many people here have seen VC dimension? Okay, so not too many, but maybe you'll be encouraged to learn about it. This is something which is used a lot in, so it comes from combinatorics, and it's used a lot in learning theory and in computational geometry, but here I'm going to talk about connection to graph algorithms. So let me give a quick introduction to VC dimension, and sort of if you don't get it, think about it as an advertisement for it so that you are more motivated to go and learn about it. But basically, what is a set system? It's something simple. You have a base set X and the collection of subsets R over X. So that's a set system. And if you have a subset Y of X, it sort of induces a set system. Basically, you take Y as a base set and you intersect Y with all elements of R to get the subsets. So it's a very natural thing. And then R shatters Y if the subsystem you get includes all subsets of Y. So this is a very abstract but fairly straightforward definition. And XR has VC dimension of D if D is the smallest integer such that D plus 1 subset of X can be shattered. So sounds very abstract. Let's see an example. And the sort of canonical example is points on the plane and half planes. So you sort of want to learn a set of points of the plane with half planes in learning theory. So the VC dimension, it turns out, so your set X is all points on the plane, and half planes is your connection of subsets. And I claim that the VC dimension is 3. Why is that? It's because any 3 point, this is proved by picture, you sort of can get all the subsets. It's sort of, this doesn't completely prove it, but it should be, it should give you the idea how proof should go. But if you have 4 points sort of in general position, with a half plane, you cannot separate black points from red points. So VC dimension is 3. Okay, and so how does it relate to shortest paths? And here we're going to use our assumption that shortest paths are unique. So we define a unique shortest path system as the base set is the sort of vertices of the graph, and then consider some collection of shortest paths. Identify each shortest path with its set of vertices. That's a unique shortest path system. Okay, it's just some subsets correspond to some collection of shortest paths. Okay, and then you ask sort of a funny question: what is the VC dimension of such a system? And once you ask it, the answer is very simple. It's at most 2. Why is that? If 3 points are on the same shortest path, sorry, if the 3 points are not on shortest path in your collection, then you cannot get all 3 of them intersecting them with the shortest path. If they are on the same shortest path, you can, because of the uniqueness, which is important, you cannot separate the red points from the black point. Okay, so VC dimension is at most 2.
Can I ask a question about the definition of the problem?
Okay.
I was confused about the definition of R. R is the set of vertices on shortest paths.
You take some collection of shortest paths.
Meaning, you give me SITI pairs. You compute the shortest paths. Now I have a collection of shortest paths.
Right. So each set, so R is a collection of sets. Each set corresponds to vertices on some shortest path.
I see. Okay.
Okay? Yeah, sorry.
Yeah.
Okay, and then this should be clear. It can be any collection of shortest paths which gives you R. Okay, so it turns out that this is useful in preprocessing algorithms. And so now we're ready to define highway dimension. Also, it explains why we define highway dimension sort of in terms of set systems. There's an underlying set system there. So we need more notation. So we assume that G is connected and every edge is the shortest path between its endpoints. Otherwise, we can just throw this edge away. And just to simplify notation, not to carry maximum degree in the formulas, we assume that maximum degree is constant, and L of P will denote the length of P, and we denote network diameter by D, where we scale everything so that the smallest edge has length 1, smallest non-zero edge length is 1, and then D is the diameter. And P sub R will denote on shortest path of length greater than R. And B sub R of V is just a ball of radius R around V. So this is sort of a discrete analog of the ball. And the heating set for a set system is a subset of the base set which intersects every set in the collection of sets, every set in R. And the distance from a vertex to a path is just the minimum of the distance between the vertex and vertices on the path. So these are all natural definitions. And then a neighborhood system, it's essentially a set system. We take neighborhood system S sub R of V is collection of all shortest paths of length greater than R, which are distance at most 4R from V. Okay, and it will be clear why we define this way. Okay, so now there is another thing, and this is something new, something which is not in our previous papers. And this has something to do with when you think about a graph, especially about a road network, you think about sort of a continuous graph where actually there are addresses on every street. So they're kind of intermediate, implicit intermediate vertices in the middle of every edge. And in real, then when you abstract it as a graph, this sort of intuition goes away, and sometimes you get funny side effects. And to deal with that, we need to define our long edges and deal with them in a special way. But it's very simple. In fact, we had to deal with these edges in implementations and then analyzing algorithms, and they always were pain in the neck. So this is a simple way of getting rid of this pain in the neck. So an R long edge is just an edge of length greater than R. And we modify the definition of heating set to define R heating set. So where we require both ends of R long edges to be in the heating set. And if you are in continuous graph, it's clear why it needs to be that way, because you can sort of place a vertex in that edge to force one of the endpoints to be in the heating set, if your heating set has to include only the original vertices. Okay, otherwise you just think about treating these long edges in a special way to deal with them. And so once you have that, there's this natural thing which you have in continuous graph.
I got confused
Yes?
as to how hitting sets are being used.
They're not being used yet.
No, I know, but you said to think of that. I mean,
Yeah. Okay.
the set system you're talking about is the set of paths, set of shortest paths. That's how
Yes.
the set system is being used.
Right.
Okay. And the hitting set is a set of subsets that intersects with every set in the set
A
system.
heating set, no, it's a subset of vertices which intersects every shortest path in that system. A heating set is a subset of the
So
base
it's the
set,
base
and
set.
vertices are the
Yeah.
base set.
And now this definition is saying
If there is a path which includes a long edge, I'm basically forcing you to take both ends.
got it.
Okay. Okay, and so this lemma sort of shows that your intuition from continuous world carries over. And it says that if C is an R heating set of some subsets of paths of length greater than R, and V is an endpoint of one of these paths, then there is a W in the heating set at distance no more than R. Okay, and oh yeah, I guess I'm also, this is new, so I should correct it. I'm also making an assumption that if some path of length greater than R is in S, and there is a subpath of this path which is also of length greater than R, then it's also in S. This will be true when we'll really use this set. And so the idea is as follows. So consider some path which goes outside of ball of radius R from V, and consider the first edge which crosses the boundary of this ball. So if it's not a long edge, then consider this path here. It must be hit, so there must be some U on this path. And if this is not a long edge, it's inside of ball of radius 2R. On the other hand, if this is a long edge, then both ends must be hit, and then there is actually a point within a ball of radius R. Okay, and this turns out to be a very useful lemma. And it's sort of, when we didn't have this requirement, we didn't have this lemma, and the result that a small highway dimension implies small doubling dimension I'm going to talk about wasn't true. So now with this lemma it's true, and it's a very intuitive lemma. So, oh yeah, and if you have a good heating set algorithm, it turns out there's an easy reduction to convert it into a good R heating set algorithm. By good, I mean polynomial time with good approximation ratio. Okay, so our definition of highway dimension is motivated by the fact that the transit node algorithm works, namely for every region, there's a small number of points which cover all sufficiently long shortest paths. So we formalize it in the following way. Intuitively, we say that on every scale, a small heating set covers all sufficiently long shortest paths close to V. And more formally, for every scale R greater than 0 and every vertex V, there is an R heating set of size H covering all paths in P sub R. Sorry, in S sub R. And remember, S sub R are all shortest paths longer than R, which are at distance at most 4R from V.
Covering means intersecting.
Heating, yeah. It hits all, yeah, heating is better here. So, okay, so think about this as San Francisco, and these are all long shortest paths. Okay, so what is doubling dimension? How many people have seen doubling dimension? Okay, again, this may be new to you. Okay, that's the doubling dimension is actually a fairly established concept, and it's basically a generalization of dimension, like two-dimensional space, three-dimensional space, to in metric spaces, and in particular metric spaces induced by graphs. And many algorithms for problems which are hard in general are simpler for spaces with small doubling dimension. And the doubling dimension is a very, very natural thing. A metric space has a doubling dimension of D. If for every R, every ball of radius 2R can be covered by 2 to the D balls of radius R. Okay? So, so in Euclidean space, you can sort of see that ball of radius 2R can be covered by probably 4 or 3 or 4 balls of radius. No, probably 4 balls of radius R. Okay, and the theorem says that in fact our new definition of highway dimension is actually strictly stronger than the definition of doubling dimension. And more precisely, if GL has highway dimension D, then the corresponding metric space has doubling dimension at most log H plus 1. Okay? And so it's actually, we are not using this theorem to prove our results we want, but it's nice from sort of philosophical point of view. It shows that our definition is a strengthening of doubling dimension. And we know that since on planar grid graphs, which have doubling dimension of 2, the algorithms don't work so well, you know that you need something stronger to assure that algorithms work well. Okay, so let's prove this theorem. The proof is we want to cover a ball of radius 2r around V. So take the following set of R ball centers. So we need balls of radius R. And we take the vertex V itself, and then we take the heating set for S sub R over 2. Remember when we talked about S sub R, there was a constant 4 involved in there. So here we're talking about ball of radius 2R, which is exactly what we want to cover. Okay, and then the size of S is, of course, if Highway dimension is H, it's at most H plus 1. This is the extra vertex. And then if V is in B sub R of V, it's covered because we included V in there. And if W is in B sub 2R but not in B sub R, then let's consider there is a path of length longer than R from W to V, right? The shortest path. And it must contain, by that lemma, we had a vertex at distance at most R. It was 2R in the lemma, but here it's R02, so a distance at most R from V. But that means that W is covered by the ball of radius R around U. Okay, so it's a strictly stronger definition. Okay, so...
Andrew, could you state the definition of highway dimension again? Sorry.
Sure. So for every R greater than 0 and every V, there is an R heating set of size H covering all this paths in this set. And there will be a proof in a couple slides which will sort of explain why we defined it in this way. Because actually what we need in our constructions are sparse shortest path covers. And an RK shortest path cover is essentially it's all paths in P sub R can be hit by a sparse set. And formally it's a heating set C, R heating set for paths longer than R, such that it's sparse in the sense that if we take any V and intersect C with ball of radius 4R around V, it contains at most at most K vertices. So it's very similar to highway dimension, but it's a global object. It's a global heating set which is locally sparse. Okay, and the theorem says that if G has a highway dimension H, then for every R there is an RH shortest path cover. And this sort of shows why we define things the way we define things, so that we defined it so that this proof goes through. And the proof is as follows. We show that the smallest R heating set of P sub R is sparse. Okay, and suppose it's not, then there is some V such that S prime of V, which is S star intersected with the ball of radius 4R, is big. It's bigger than H. Then notice that vertices in this set hit only paths in S sub R of V. That's why we define S sub R of V that way, right? Because they live inside of this ball, so every sufficiently long path covered by this set must touch this ball. Okay, and we defined S sub R of V exactly in this way. So let H be an R heating set of S sub R of size at most H. We know by definition of highway dimension there is such a path. But of course everything covered by S prime of V is covered by H. So we can replace S prime of V by H and get a smaller heating set for P sub R, or R heating set of P sub R. And this is a contradiction because S star was the smallest one. So the smallest one must be sparse. Okay? So that sort of explains why we define things in this way. And now finding a star is NP hard. And if we want to put our theory hat on and say that we want polynomial time preprocessing, what can we do? And our original paper showed that there is an order of log n approximation, that the greedy algorithm gives an order of log n approximation for finding a star. And the question was for a year or so is whether we can find approximation independent of n. And it turns out that we can, using that result about VC dimension and shortest path I showed you. And first notice that if we have a polylog time, some constant times log h approximation for the heating set, then we can get R order of h log h shortest path covers. And the proof is it's essentially we notice that this proof is sort of constructive, and by replacing exact thing which we cannot find by approximate h, we can make this proof constructive in the sense that if this set is not sufficiently sparse, we can find a smaller set. And we can keep doing that until this heating set will become sufficiently sparse. And since each time we reduce the set size by at most 1, in at most n iterations will be done. So we can use a subroutine which gives an h log h approximation. So we need an order of log h approximation of a heating set. And it turns out, conveniently enough, that people in computational geometry had such an algorithm. So there is a result, there is a sort of learning theory algorithm of Clarkson, which is randomized, which was de-randomized by Brunigan and Goodrich, and also there is an LP relaxation-based algorithm of Evan et al., which prove the following theorem. If you have a set system with optimal heating set of size h and VC dimension d, then in polynomial time you can find an hd log hd heating set. Okay? And actually this is a nice application of boosting. And this is not an algorithm as I would, not the first or the second or probably even the third algorithm I would try as graph algorithm designer. But turns out it works, yes?
You said that, I got a question about the intuition. So my intuition, so you were saying finding these, I forget what you called them, but the groupings you want to have these shortest paths, like what are the clusters and what are their external points, is hard, right?
Finding S star was an smallest heating set for.
Right.
So yeah. So in general, finding heating set, it's basically you reduce it to set cover, and it's hard.
Yeah, and the point is that if you want to keep the small, it's some global smallness of the entire graph property, right?
Mm-hmm.
But my intuition from the other stuff you said is that the points you actually care about should be a local I mean, you should be able to, like take any small area, like it should be a local property, which are the...
Yeah, so shortest path covers are a funny thing. They're a global object with a local sparsity property.
Exactly. And so it seems like just like finding these, like who cares about the global properties at all? Just look at find the sets with the local property, and then can't you not?
Maybe, but we are using the shortest RK shortest path covers in our algorithms. Maybe we can use directly the definition of highway dimension, but we are using these things. They're sort of natural to use because now it's actually more clear, because when people designed approximation algorithms for shortest paths on graphs with small doubling dimension, they were using so-called epsilon nets, which are sort of close to the shortest path covers. So it makes sense from this perspective. Maybe you can do it in another way. I'm not saying you can't, but that's what we're using. Okay, and then since D in our case is 2, we get the result we want, right? This Okay, and so now we'll talk about, we want to go back and analyze transit node algorithm and also some other algorithms. So let's start with sort of preprocessing we need for these analyzable algorithms. And it's very simple. So let's say that k is either h or h log h, depending on whether you allow preprocessing to be exponential time or not, whether you worry about efficiency of preprocessing. And then what we do is we, for every I from 0 to log d, we compute 2 to the I minus 1 k shortest path covers. Okay, notice that if I is 0, this is 1/2. And since we have a k heating sets, it means that every edge which has length 1 or more, both ends must be covered. So V0 is a set of all vertices. And we can prove that as you go up, the number of vertices in the set doesn't shrink too much. It shrinks by at most k, and at the high level you have at most one vertex because basically you need to cover the diameter, and you have at most k vertices. So this is relatively easy to prove, and it basically shows that these things, sizes of these things sort of don't change by too much at every step. And so this is the preprocessing. We just compute these things for log d values. And the preprocessing algorithm for transit node algorithm works as follows. So we pick t so that t squared is not too big. Remember, it was 10,000 in the example. You can make it, say, square root of m. Then the size of the table you need to store will not be bigger than your graph size. In practice, if you can afford more memory, you'll use more memory, right? But you pick some value of t, and then you pick little t such that the size of the CT you computed is at most t. And you pick the biggest c sub t in this way. And since they don't grow too much, you'll get something which is close to t in size. And then you let c sub t be the set of transit nodes. So these are the things in this shortest path cover. And then you just do the normal preprocessing. You compute the distances between transit nodes. But to compute access nodes of a node A, you do of a node V, you do the following. You build the shortest path tree from V, and then you sort of start at V and go along the tree on some path until you hit the first node in this cover. Then you forget about this branch rooted at this node and follow some other path, and so on. So basically, you take elements of C sub t, they're all on the tree, right? This is shortest path tree of the whole graph, but you pick the ones which don't have anything between V and them on the tree. If V is in C sub t, then just V will be its own access nodes and nothing else. Okay, so this is preprocessing. Given that you computed this C sub i's, this is clearly polynomial time. And then this size of the number of access nodes of a vertex V is at most k. And that's fairly simple. This is just essentially by construction. Remember that we have this lemma about a path of length at most t, which must be covered. So if you look at the tree on a path from V to X access nodes, it doesn't have any more other access nodes. So if you go from V to W, W must be close to V. And close, since we use t minus 1 in the definition of C sub t, its close means 2 times 2 sub t. And so it means that W is in this ball, which means that the number of such W's in the heating set is small. It's at most k, because because C sub t is the shortest path cover. So we have analysis of the transit node algorithm. We know that the global queries take at most k squared time. And remember, k is either h or h log h. So it's roughly the square of highway dimension. Okay, and that's assuming that road networks have small highway dimension. This is something small. In particular, if highway dimension is asymptotically less than square root of n, then this is sublinear. Okay, we're not quite done in that transit node algorithm. Remember, I told you that local queries you answer differently. But how do you know what is a local query and what is a global query? So that paper had sort of a hack for it. They say, okay, we sort of know that we're dealing with maps, and for every node we also have coordinates. So we know Euclidean distance between the nodes, and also we know the maximum speed with which you can travel, so we can compute distance estimates and know what's close, what's not, based on this sort of additional stuff. But suppose you don't know Euclidean distance and so on, what can you do? Well, it turns out that our algorithm actually also gives this what so-called locality filter. So notice that if G is the value computed by the global query, that algorithm I gave before, then if distance between S and T is greater than 2 to the T minus 1, then we know that ST pass has an element of C sub T on it, and we know that the query will be correct. Okay, so if the distance is sufficiently big, the query will be correct. Suppose the distance is small, it's less or equal to that. Well, we show that G sub T cannot be too big. So the problem is if the distance is small, the shortest path between S and T may not have any elements of C sub T on it, right? But on the other hand, the worst that can happen is we sort of go 2 times 2T minus 1, namely 2T steps away from T from S. Sorry, T was an unfortunate choice. This T is different from this T. Sorry about that. This T is just some number, and this is a vertex. That happens with new slides. So this is the difference between an upper bound and distance between these two vertices. And this is how far away you go to the first transit node, and this is how far away you go to the other transit node. So the value you get must be at most 5 times 2t minus 1. So it turns out that if this global query returns a value greater than 5 times 2t minus 1, you know it's correct. And if not, then you need to do a local query. Okay, so we have also a nice justifiable way of doing local query without, of locality filter without knowing the coordinates or anything like that. Okay, let's go to hub labeling algorithm. And generic preprocessing, you do, a hub labeling algorithm, the idea is that for every vertex you compute a label, and labels are enough. You forget about the graph then, and you use labels to compute distances between vertices. That's the general idea. And a particular hub labeling algorithm, you have the following labeling property. If you intersect two labels, label of S and label of T, then they intersect, and intersection contains a vertex on the shortest path.
What's the size of LV?
That's an interesting question. I will get to it. Yeah, so the query algorithm is then simple, and it's efficient if this label is small, right? It's very easy for every vertex, make all vertices to be its hubs. Then this property is trivially true. But a query takes order of n time, which is not that interesting. So queries are efficient if labels are small. And now we show...
The label property, there exists a vertex in the intersection.
Yes.
That's on the path.
Right, so you have to look at all.
There could be other vertices too.
Yes.
So then you exhaustively check each vertex.
Yes.
To find the one with the minimum distance if you go...
Minimum sum of distances.
Mm-hmm.
Right. Right, but if this intersection is small, then you are fast. Okay, and we show that if highway dimension is small, then you have small labels. Okay, and preprocessing, first of all, you do the same C sub I as before, And then label of V is the union of C sub I intersected with ball of radius 2 times 2 to the I of V. Okay, and each of these intersections is of size at most k. So the union over order of log d values is order of k log d. So that's the label size. And then for correctness, it's sort of easy to see that if p is on the scale of I roughly, then both this shortest path between endpoints S and T of P contains an element of C sub I, and they're both in this ball, so they will have a common element. Okay, so preprocessing with polynomial time preprocessing, we get k log d, where k is order of h log h query time. And query, what we can do is now we're talking about something like, remember we talked about 100 memory accesses, so it's important that these accesses are local. So what we can do is we can sort a label by vertices in the label by hub IDs. Okay, and then we have a problem. We have two arrays which are sorted, and we want to find the intersection of them. And it's easy to see that if you do sequential sweep like in merge sort, you can find the intersection. And the nice thing is that you get essentially perfect memory locality because you go through arrays sequentially. And it turns out that distance queries turn out to be less than 300 nanoseconds. And this is because labels will turn out to be small. So now we wanted to implement this algorithm. And sort of before that, people thought that, well, it's unlikely to be practical because suppose you have a road network of US with 30 million vertices, how big the labels are. How many vertices do you need to know to go everywhere? And people thought probably a few thousand, and that's too much. But in fact, it turns out to be about 100, which is much better. So theoretical preprocessing, unfortunately, is impractical, so we used theory-guided heuristics and some new ideas and careful implementation, and we turned out to have 4-minute preprocessing, and average label size turned out to be, in our original paper, 85 for a certain graph of Western Europe. And recently we reduced it to 69. And that's sort of how these labels look like. Okay, so we have some other results, and since I'm running out of time, let me skip those and show some experimental results. So this is sort of last 10 years in the area. So there's Dijkstra's algorithm, which actually this is the fastest server. It takes about 2 seconds, not 5 seconds, as I said before. And this is alt is a star search with landmarks. It's something we're very excited about because it sort of reduced running time by almost 2 orders of magnitude. And of course, then we came up with reach algorithm, which gained another order of magnitude, and we were happy about it until people in culture came up with something which was 5 times as fast. And then they made us really depressed because they brought the time down to 94 microseconds. And then the transit node came, and it was 1.8. And that looks like you cannot beat it, right? It's 100 random memory accesses. But it turns out that HL is less than 300 nanoseconds. So it's even faster. And in some sense, it's a horse race because this is just distance query. If you want to actually output the path, which has several thousand of vertices, it will take you longer than that. But sometimes you only need distances. And in any case, it's nice to have the fastest horse. So things are a little bit more complicated. This is a measure of locality. So let me not explain you, but this is more local queries and this is more global queries. And you can see that contraction hierarchies algorithm I sort of didn't talk about, but it's important. It has some very important ideas. It's sort of, as most algorithms, sort of the more global query is, the longer it takes. But this is multi-level transit node algorithm, and it has this counterintuitive thing that global queries are faster than local queries. That's because they have this nice form, right? The labeling algorithm is fairly independent of locality. And the nice thing is that it's much better than transit nodes for local queries. And in most applications, queries are fairly local queries. You rarely go cross-country, but you often go to the next town or something. Okay, so this is sort of nice curve, and it's actually, for some tail reasons, it sort of is a little bit faster for global queries, but not that much. Okay, and so it's about time to finish. So there's some research directions, namely complexity of computing shortest path for small highway dimension networks. We know it's hard in general, but maybe for small highway dimension. It's not that hard. Probably it is, but you have to prove it. And then
do you think we can parameterize with the HD dimension, with the HD?
Probably, yeah. Practical algorithms for computing the shortest path covers, probably good shortest path covers. Other applications of highway dimension shortest path covers. For example, assuming small highway dimension, can you do something for TSP as where highway dimension is a parameter? And then the dynamic and time-dependent shortest path algorithms. And let me emphasize the nice thing about this work for me was that there was sort of a use of scientific method, in a sense that there was experimental observations that several algorithms are really fast in practice and the number of transit nodes is small. And then we came with highway dimension as an explanation for why this is the case. And we predicted that the hub labeling algorithm will be fast. And in fact, we verify that it is fast. So this theory is now sort of more, at least it was useful. Maybe it's not quite correct, but at least it allowed us to make some advance in the speed of these algorithms. Okay, so that's it. And by the way, this is our project page, and you can get papers, except a couple of results I mentioned will be in the journal version of some of these papers. Not there, but most of the results are there.
Are there any more questions? All right, thanks, Andrew.